pequeño retrasito. And I think, let's check. Cool. I think we are live. Welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host today. Today, we're presenting Tidal Deformation of Black Holes by Maria Jose Rodriguez. She received her bachelor's in physics from Universidad de La Plata in Argentina, and then she moved to Spain, where she did her master's and PhD from Universidad de Barcelona. Then she did a couple of postdocs at the Max Planck Institute in Potsdam, and then she joined Harvard again as a postdoc before becoming a professor at Utah State University, where she is now. She's an expert on strong gravity phenomena and many things, including, for example, universal aspects of the quantum structure of black holes and event horizons. And today we'll have a glance of one of her latest interests related to black holes. So remember, you can ask questions over email, through our YouTube channel, Twitter, or X, and then the questions will be read at the end of the talk. So without further ado, we will turn it over Maria, and thanks for joining us.
Thank you very much, Alejandro, and thank you everyone at the Law Physics seminars, the Latin American webinars. It's a pleasure to have the opportunity to talk to you today. Let me start by sharing my screen very quick. So is it okay? Okay, sounds good. Okay, perfect. So my talk today is about dynamical love numbers for Kerr black holes. This sounds like a very technical talk, which we are going to slowly work out a way to understand what the topic is about. But the message, or the short version of my title, should be deformations of black holes by other gravitational objects in the universe. So this is what my talk is all about. So, okay, it's not, okay. So the outline of my talk will consist in 3 parts, mostly. One first motivation and introduction to the topic of tidal deformations of black holes. This will be a more colloquium style. We'll show you a bit why I got interested in these ideas that became popular, I think, in the last 5 years, especially in the theoretical community. I will then go on in like the more technical parts of the talk, which are going to be an overview or review of what we call the static love numbers, or the static deformations of black holes. And then the last bit of the talk will be about dynamical tidal deformations of black holes, something we did together with Malcolm Perry in this paper a few months ago. So that is the outline for my talk, and I hope that if you have any questions, you just ask, and I'm happy to give you my views of what I know about the topic. So tidal deformations is something that we are very familiar with, especially here in our world, in our planet, which is the Earth. So tidal deformations in general for these talks are going to be the gravitational phenomena that causes bodies to stretch along the line pointing towards and away from the center of mass of another object. So we have the Earth. And in principle, the Earth and the ocean are typically not, if they weren't embedded in another field, they would be just round spheres. However, we see that because of the existence of the moon and, of course, the sun and the other planets, but specifically the moon in this example, you could see that there's a deformation of a very evident deformation of the liquid or the ocean, which is and forms the tidal bulge, and due to the gravitational attraction of the moon towards the ocean. And in particular, there's also one on the solid a bit, but it's so small that you cannot paint it in this graphic. So the result of the spatial variations of the gravitational field in which the Earth is embedded, brings or has an effect, which is a tidal deformation, a deformation due to the existence of another body next to it that causes this. And of course, when you were young, you experienced waves in the ocean. So we know that tidal deformations have effects. They create, for example, our waves in the ocean as well. So it's a real big phenomena. And effect in our world. So what happens out there? Well, we also observe that tidal squeezing or tidal deformations exist within our solar system. This has been really looked up, and in particular, there are very big effects that we can and we have been studying quite a bit for Jupiter and one of its moons, that is Io. So Io is a satellite in Jupiter's system that gets really deformed due to the gravitational attraction of Jupiter. And it causes also very big effects in the precession of the orbits and as well as the deformations of these objects. So tidal squeezing is not only an effect that we see in our planet, but we also see it within our solar system. Now, newer data and information, we have become so good at measuring, many things also not within our solar system, but in other systems, have also detected that there are other planets, exoplanets, so planets without being in our system, solar system, that have also or suffered tidal deformations. And so this is one of the examples here where there's a host star and you have one of the planets surrounding the star is really more like American football sort of planet instead of this round sphere that we typically think about in our planets. This tidal squeezing, something I did not mention for some of the planets in our solar system and beyond, would also contribute to effects like volcanic eruptions. Because of the squeezing, we know that internally some of the planets have a liquid core, and that is what produces volcanic eruptions as well. So tidal deformations is something that is very frequent. So the effect of gravitational objects into other objects. And one of the questions one starts to think about is what is the scale of this tidal deformation? So what I'm showing you here is another system where we see two galaxies. So this is the Seyfert galaxy NGC 169 and IC 1559. And we see also here that there's tidal deformations at this scale, so very big scales in which effects of the tidal deformations are very, very evident, and we can also start seeing them. So what happens is that these effects will also be present in other objects. And in particular, they will have different contributions or effects or that we can measure. And so one could then ask, what is the composition of the objects? Because due to I was discussing solid versus liquid cores, they will undergo distinct deformations. And so we expect that we can learn as well, not just the tidal deformation per se, but also what those objects are made out of, or what is their internal composition. So here is another way of looking at tidal squeezing, and this is a more mundane effect. But I wanted to represent in this picture, these are giant squashes that you see around farms when, for Thanksgiving, and there's the more spherical ones. So the internal structure of the objects will create different deformations in the presence of the gravitational field, which in this case is the Earth, right? Okay, so I leave you with this idea of the squash way of thinking of objects to start thinking about black holes. And that is kind of what the context I wanted to set up, because at certain point we were thinking about tidal deformations, and we looked a way of describing stars in particular and galaxies. But one of the questions that came up was, what were the effects of the gravitational deformations in black holes? So that is what mostly my work has been focused on in the last year, and what we are going to now be discussing. So fundamentally, the idea is very basic. So typically we describe one black hole, and that is what we are interested in, and we look at their effects in their environment. But we also know that black holes come in binary systems. So one of the questions one could ask is, what is the tidal deformation of a black hole that is embedded in a system where there's another black hole or another gravitational field that will deform the geometry that we have essentially as an object that is not embedded in another gravitational field? Well, one of the questions that first we would like to understand in this idea of a black hole being sort of like a pumpkin is that we don't really know what the black holes are made out of. And so some ideas have this statement about black holes, that black holes are nothing, and they're simply boundaries of space-time. So if we take that concept of this boundary of space-times, well, in the presence of another gravitational field, should they deform or not? And if they do, how do they deform? And could we, in principle, start thinking about what are they made out of, okay? So one or some of the ideas behind these studies of tidal deformations, one can have, and I will show you a few pictures of different ways of thinking about them, but those are sort of the questions about black holes that we would like to answer one day and start thinking about them in a more perhaps different or better way, because black holes are embedded in other gravitational fields. So let me move forward. Okay, so tidal deformations we have seen are plenty in different scales in different places on our galaxies. But what I'm showing here in the bottom, which are the new pictures that I wanted to bring in, are explicitly numerical simulations of the deformations. And here, even though it's painted in yellow, this is the merger and the event horizons that of two black holes that are merging, that are going closer to each other. And so the event horizons are topologically becoming a toroid. So they are not longer two black holes, but they do have in these numerical simulations a joint, if you want, tunnel between them. And we can observe that they are tidally squeezed or deformed. Another way of seeing this, so this is binary system that is in an orbital motion merging. And this one here is a tidal squeezing, so tidal deformations, numerical simulation when one has a head-on black hole collision. So you see the two black holes are typically round, and as they start approaching, they do produce this link between them to finally merge. And this is a numerical simulation for the head-on collision. So we have that data, we have that information from the numerical simulations that tidal deformations of event horizons, which is important in this case, are really true. So one of the ideas was to try to see how much we can do analytically to describe them and see what those tidal deformations are, and try to understand other properties. So I mentioned internal composition of squashes or planets and so on. For black holes and neutron stars, this could be very interesting because we don't really know what they're made out of, and so we would have or be able to contribute a bit to that eventually. This is not what my talk is going to be about. This is part of the motivation of why tidal deformations should be interesting to see. In particular, if these objects are now emitting gravitational waves, and they're not now two round spheres, but they become these deformed topologies of event horizons, well, then those gravitational waves should also show information about this structure that is not now two spheres emitting gravitational waves, but a deformed topology, tidally deformed black holes emitting gravitational waves. So what I'm going to now discuss is not this extreme already connected type of tidal deformation for black holes. We are not yet there, but I want to do, and I will describe now this with equations and more precisely, how do we describe the tidal deformations of the black holes? Not when they're so close that they start being connected, but even a much more simpler problem before they're connected. And so let me flesh that out. So what we are interested in is in the tidal deformations of one of the black holes. I will ignore whatever the other gravitational field is in the approximations. But what I will show you is that, in fact, all we need to do to find some of the perturbations in the geometries for these tidal deformations will become or will be resolved by looking at the wave equation for fields in the background of a black hole, say a Kerr black hole, or any other object. If you're in higher dimensions, it could be a black ring or a Myers-Berry black hole, etc. So what you're going to see next is how we are going to be defining through the wave equation a perturbation, a gravitational perturbation on the geometry through the wave, if you want, or your scalar in here. And we are going to be looking at these coefficients here, which will become these coefficients that define our tidal deformation. Okay, so this is only kind of to show you where I want to go to in one slide. So how do we define, or how do we get to that equation that we need to solve for the tidal deformations? Well, in general relativity, we can look directly at the metric perturbations for this description of the tidal deformations of rigid objects. And what we want to find is if we have a geometry that is going to be our tidally deformed black hole, G mu nu, we can think about this tidally deformed black hole as not, a very tidally deformed black hole, but rather a metric I said here flat space, but in general, you could write a Schwarzschild black hole or a Kerr black hole geometry, and some perturbation, h mu nu, that is going to be the perturbations, the tidal deformation perturbations to your geometry. So in some way, what you have is a geometry that exactly will solve Einstein's equations plus a deformation. And what one does is one plugs in, or one tries to find solutions of a tidally deformed black hole as a linear perturbation to the geometry. And so one linearizes the Einstein's equations in this case for this tidally deformed geometry, and ends up, roughly speaking, choosing, better ways of gauge choices and reshuffling of the geometry with an equation like the one you see here, in which this box is basically the Laplacian, or the curved Laplacian in some of the cases. But in the end, what one has is that, is the equation for the perturbations that are needed or need to be found so that one can describe the tidal deformed black hole. So these perturbations perturb all the terms in the geometry, but in particular, one of the focus of what those deformations are is in the TT component. So one of the components of the geometry, the perturbations, is this TT component. And in general, we know that this component decouples from the rest of the perturbations. And actually, we know more than what happens with the other components of the perturbations. But here I will focus only on the TT component. And so in the end, what happens with this perturbation is that the perturbation divided by 2 is essentially a scalar function. And the reason why I identify the perturbation with this is because the linearized equation I was discussing in the previous equation becomes basically, for the TT component, Tsiolkovsky's equations in the background of, if you had Kerr that you wanted to tidally deform, well, it will have, or it will become the Laplacian of the Kerr black hole for your scalar function. So instead of having, or we simplified in some way the perturbations that we want to find for the tidal deformation, we reduce the equations, and in particular for the TT component, it becomes this much simpler wave equation for a scalar in the background of a black hole. And that is what we are going to be solving. So in the case of black holes, what we are going to find is that the perturbations are going to have a decomposition. If we do say a decomposition in R, in the radial directions, we will find that the first term contributing will be a central mass, so a potential as a point particle, and then other contributions that will have this form here, and I will be more precise of how this happens for the perturbations. And some of this behavior will give us some universal quantities that are going to be called the tidal love numbers, these KLMs, that are going to be the coefficients, the tidal deformation coefficients for the black holes. So what we need to go is to go back then to find the tidal deformations and try to solve the wave equation for a scalar. So now the difference, if you want to think about black holes, is that we are told at school that black holes should be described by the solutions found by Roy Kerr, so by Kerr black holes, if the black holes are spinning. Well, now the idea is that, in fact, to characterize black holes embedded in other gravitational fields, one will have not only the mass and the spin parameters as in Kerr, but also the perturbations that will give you these tidally deformed black hole objects that one has to think about. So the tidal deformation problem for some of the components of the perturbations are going to be resolved by looking at the wave equation. So how do we do that? Well, in general, we will have to solve this equation. And one of the magical things that happens in the Kerr black hole background is that we can propose an ansatz for our scalar field and see that, in fact, this is a separable equation, meaning this Laplacian equation here, with this ansatz like this for the scalar, in which we have some characteristic values or eigenvalues here of omega and m. And in the end, we end up with two equations, an equation for the radial part and the spheroidal part. In Kerr, we know how to solve, to a certain degree, the spheroidal equation. So most of the focus will be in what is the solution to the radial part of the equation for this wave equation in the scalar equation. And I'm sorry, I didn't mention, but S here is a general scalar with spins that are integer numbers, 0, 1, or 2, representing a scalar, and 2 for example for the gravitons. So once you find the solution in principle of these radial equations, one needs to set up some boundary conditions to define the tidal deformations. And what we want is a deformation that is ingoing, or is, if you want, smooth along the boundary, so of the boundary of the event horizon. And so the fall-offs that we are going to take as valid fall-offs evaluated at the horizon are the ones that take this form and become smooth or ingoing at the horizon. And then once that is set up like that, we'll take and make an analytical continuation of that function that we picked. We will have, in general, for example, this is second order linear differential equation for the radial equation. So there will be two solutions. And so with this boundary condition, we will set one of the constants in the linear combination for both to be 0 and pick the one that is smooth at the horizon. Analytically continue, which is basically say that the range in which the validity of this solution is approachable is in a regime where we can extend it to infinity. And so by the analytical continuation of the solution, we'll see that the behavior of the solution at infinity takes this form. And so the characteristic is that the functions for the wave function will go like r to the L times, and in this product, we will see 1 plus r to the minus 1 plus 2L. And the coefficients here are going to be the dimensionless characteristic effects that we will see in a tidally deformed black hole. And these are the tidal coefficients or love numbers that people have been referring to. So this is the definition that we will take, and this is what all the analytical discussion about love numbers have been looking at or discussing when you read the papers. But it's necessary at this point to make classification. There are going to be two types of tidal coefficients. So these KLMs can depend or not depend on the value of omega, of the frequency, yes? And so the static love numbers are going to be ones in which the black hole that we are going to be focusing on is embedded in a static gravitational field. So the field generated by the external black hole or system is going to not depend on time. And so there's a lot of work and there was a lot of discussion about the static love numbers. But then there's a second class of love numbers, and this is my production of a movie in which the objects are moving. In particular, the tidal deformation will, or the external source will have a time dependence. And so the KLMs, the tidal deformation coefficients, will depend on omega, on the frequency, yes? And so those are going to be the dynamical tidal love numbers. And we will see that the static love numbers versus the dynamical love numbers that we are still trying to compute rigorously are and behave very different. And in particular, a lot of the discussion in the last 3 years was about the vanishing of the love numbers, but the reference of the vanishing of the love numbers will be mostly about the static cases. And in fact, now that we have been studying the dynamical tidal love numbers, which is what I did with Malcolm and other groups have been looking at as well in the last years, we'll see that in fact, when the gravitational source is not static, which is a more realistic effect, because typically things in our universe and galaxies are all dynamical, these love numbers will not vanish. Okay, so that is kind of the distinction here, static versus dynamical. So KLMs that depend on the frequency or do not depend on the frequency. To make things more complicated, there's an additional classification. And so in either static or non-static, or in the dynamical cases, these KLMs can have and can be complex numbers. So it's not required that these KLMs are real numbers. And in particular, one of the real part of the KLMs, dependent or not dependent on the frequency, doesn't matter, is what is going to be the conservative effect, where people have dubbed these love numbers more specifically. And the other bit, the bit that is imaginary, is going to be the dissipative effect, okay? And the reason I'm labeling this in this way is to be more precise, to be able to tell you what vanishes and what is not going to vanish in the static case, okay? So in general, then we have static versus dynamical. This is just the omega dependence of the coefficients. And then we have a second layer, which is real and complex part of these KLMs, which gives something that we will interpret as the proper deformations. And this is going to be the dissipation, how the black hole is going to be able to radiate those effects of the tidal deformation away. Okay, so let me first focus on the static love numbers and then move to the new part, which is what my last paper was about. So this is sort of a review, but I will use this notation, and this is why I'm being careful about how I define this. So for the static love numbers, so when we put, say, the Kerr black hole in a background that is not moving outside of this object, there are tidal deformations. So the KLMs are not going to be in general zero, and they're going to be in this way. And these KLMs that are static, so they don't depend on the frequency, have a real and an imaginary part. And it will be the real part of these numbers which are going to be zero. And this is what everyone was talking about the vanishing of the love numbers. So in effect, for the static computation of the tidal deformations, the love numbers, the real part of this KLMs do vanish exactly. It's not that they're very small, it's exactly that what happens is these KLMs have no real part of these numbers, and so they vanish. Yes. The static coefficients, the imaginary part of the static coefficients do not vanish, okay? And in fact, they become this very complicated form in here, which look a bit unusual for the things that we typically see. And what are these parameters? Well, these parameters are all parameters that are either the black holes or the way we described the tidal deformation. So in here, we have R plus, R minus are going to be your outer and inner Cauchy horizons of the black hole. So R plus and R minus are the ones, the R plus and R minus for the Kerr black holes, and will depend on M and A, the mass and the spin parameter. We have other constants in here, which are L and S. Well, S is going to be, if it's a scalar, we're going to take this as the as 0. If it's S equals to 2, which will be the deformation that we will put in the geometry, that is going to correspond to the graviton in here. And these M and L's are the eigenvalues. Which eigenvalues? Well, if we go back to the equation of the wave equation, we had some eigenvalues that were related to the azimuthal direction, so M phi, when we solved the separable equations. And these L's come from the separation constant, so basically they will be related to the spheroidal separation constant in there. And so these static dissipation coefficients depend not only on the parameters of the background black hole that we are tidally deforming, but also on the eigenvalues of the full equation that we are solving for. Gamma, I didn't write that here, but gamma is also a parameter that is A, the spin of your black hole, divided by R plus minus R minus. I'm sorry about that. And so this is also dependent on R plus and R minus. So the point here in this review is to show that, in fact, when we take the spin to 0 for the Schwarzschild case, yes, this gamma here will also become 0. And so for Schwarzschild, both the static love number or a tidal deformation and the dissipation coefficient both go to 0. Now for Kerr is different, and we have this complex bit in here. And what is surprising or interesting, as we will show you, is that when we analyze the dynamical love numbers, the same form of this dissipative coefficient will show up as a repetition in the dynamical love numbers. Yeah. So the structure per se is complicated. It doesn't mean too much when I show you this, but it's going to be interesting to see that in the dynamical case, when the source is actually moving, we will see that we see this over and over again repeated in here. So this dissipative, what I painted here is this coefficient, so the imaginary part, the dissipative effects. And I just wanted to show you, if we change the values of them, I fix the mass and start spinning the black hole faster, and I fix one of these coefficients L, as I increase the spin of the black hole, the dissipative coefficient becomes larger and larger, and this repeats for all else. This is only kind of a way of representing something about these coefficients. Okay, part of the argument behind these ideas of the vanishing of the love numbers try to explain from a very symmetrical point of view, why is it that, in fact, this love number, so the real part of the love numbers, vanishes? And there are two approaches to do that, and they rely in different symmetries, okay? So I'm not going to flash out here this, but to contrast to what we are going to be proposing next, it will be necessary. So there are symmetries of the geometries that we typically work with, which we know Kerr doesn't have a lot of symmetries, but there are also hidden symmetries of this system. So what do you mean by hidden symmetries? Hidden symmetries will be symmetries that we observe not at the level of the geometry itself, but they're hidden in the fact that they're symmetries of the wave equation in that specific background. And so, for example, in the case of the Kerr black hole, it was argued that there are two different hidden symmetries that one can observe, in particular, one that is realized at the level of the wave equation, where the symmetry is SL2R times U1, also called love symmetry, that could explain that this is a symmetry that shows up at the wave equation level, love symmetry, that could in fact show that the love numbers, the static love numbers, are zero in the Kerr black hole case. And another proposal is that if there's another choice of the hidden symmetry being an SO 4,2, then this is sometimes also dubbed the Starobinsky symmetry, could also show that the static love numbers are zero. Okay, so this is all there is in the case of the static computations. And what we know is that in general, for the dynamical case, one can go and do some low frequency, low spin approximation and find these love numbers in that regime. Okay, and so in that case, we note exactly now for omega naught equals to 0 that this is the form of the love numbers in this regime. And so neither of these symmetries, hidden symmetries, could be exported to the frequency-dependent dynamical case. They were good in trying to explain the zero of the static love numbers. But if I promoted these hidden symmetries to omega dependence, they would not give you the dynamical love number that we know sort of analytically to order omega in some omega in these coefficients here, how to compute exactly. So what we did in our work is to look, and I will not mention the EFT bit, is to try to see if there was some way of describing these tidal dynamical deformations with some symmetry argument. And so instead, what we did, instead of looking at this other symmetries, we went back and took some of the hidden symmetries. So we insisted that the wave equation that we wanted to solve in the background for Kerr would have an SL2R times SL2R symmetry, instead of any of the other ones that were presented and valid for the zero or the vanishing of the love numbers. And the argument for doing that is that one can work in certain regime here where omega times m is much smaller than 1 and omega r much smaller also than 1. And here I present what the spheroidal equation is and how the eigenvalues, these L's, show up in the separation constant for the equation. So the hidden symmetry that we propose is SL2R times SL2R to compute the dynamical love numbers. And this was in some way also inspired by the Kerr CFT correspondence and trying to think that, in fact, some of the expressions for scattering in the Kerr black holes do represent or have this type of symmetries, this SL2R times SL2R. So when we did this computation in this regime, and we insisted on having this hidden symmetry for the dynamical problem, we went and computed the tidal deformations in that case. And so how one does that? Well, there's a few steps. One has to do a coordinate transformation and identify the parameters to see that in the end, the radial part of the wave equation that will have this form like this, and this omega is the function here. So I'm representing this equation here as a hypergeometric differential equation, ends up having two solutions, which are linear combinations of these two. And so, as I said, the formula or the protocol to proceed in finding this is for the two solutions that one gets, one has to fix ingoing boundary conditions and then do an analytical continuation. So this is the sketch of what one does. One sees that the second solution is not smooth on the horizon, so one throws this away, keeps this one, and does an analytical continuation. And this is what one finds in this case for what the ratio then, or the follows, is. So one can compute the ratio between one of the terms and the other, which gives you this minus 2L or RL here, to find the tidal coefficients, the dynamical tidal coefficients. So what I wanted to show you here is that the formula for the tidal deformations is very complicated. There's ratios of gamma functions, but again, they start depending on our plus and our minus in here, and there's some omega dependence. But when we go to the regimes of the previous equation that I showed, that we know exactly in the low frequencies what you get, we see that, in fact, we recover the expressions for the low frequency regimes exactly. And so what's happening when we go to higher orders in the frequency, so I'm doing an expansion of the very complicated expression for the dynamical KLMs or tidal love numbers that we find, and I'm doing this and keeping order by order. So this is the first order in omega, this is the second order, etc. Is that this zeroth order here that you see is this expression here, which is the with this product here, which is the one that corresponds to the static tidal deformation. And so what we see is that there's a repetition of that. And so the first order depends on the static one, and the second order depends through the first one also to the zeroth order, and so forth. So there's some repetition in the way the dynamical love numbers are arranged in this case. And we have this agreement with the low frequency results as well. So there's some indication that this hidden symmetry persists or is present for the dynamical love numbers. And one can go and then take all these parameters to zero to see if there's agreement for the Schwarzschild case, which is something that we are currently looking at. And then think about whether there's some way of interpreting these expressions for the tidal dynamical love numbers in the CFD. So thinking about holography and ways of interpreting these numbers. So this is almost what I wanted to talk about. There are some generalizations that one can make Sorry. So let me just go on and kind of summarize a bit. So we reviewed a bit what these ideas of tidal deformations were. Maybe I insisted quite a bit on the characterization of the static versus non-static and so forth, but it was for me complicated to go through the literature at the beginning and try to understand what was actually vanishing, which was the love number that was really vanishing. So I hope that at least I gave you that idea of how we kind of have to do the computations and how they are characterized. And then trying to argue that symmetries are a way out of what is happening in the tidal deformation processes of black holes. And they will have not only for explaining the zeros of the love numbers, but hidden symmetries will have a say in when we study the dynamical process as well. And one of the candidates or ideas in here is that there's this SL2R times SL2R hidden symmetry. I hoped we could learn more about the internal structure of black holes. So my pumpkin version of the black holes, but black holes seem to be resisting all the computations to learn about what the internal structure is. So I haven't given, my hope up, but, I can't say much about the internal structure. We're just beginning to learn about this. And and so that's all that I wanted to talk about today. Thank you.
Thank you very much, Maria. This was an amazing talk on your insights of love numbers, and I found it very informative and engaging. So let me see. So there, let me check where we can get some questions, and there will be maybe a delay, even if you
That's
answer,
okay.
then there
No
will be.
problem.
We don't know if there's a follow-up. So okay, so there's one question. I was under the impression that I guess it's LIGO Virgo collaboration measures tidal deformations as a way to distinguish black holes and neutron stars. However, at the beginning of your talk, you showed that the tidal deformability is manifested in numerical mergers. So what is the perturbation that I believe? So what is the tidal perturbation is measured by LIGO Virgo or this collaboration?
So there are different regimes in when the gravitational wave detections are, performed. And so in the gravitational wave detections that we currently have, we are not in the regime where the black holes are in the very, very strong connected regime. This is a numerical not approximation, computation, the one that was linked between that. That's not the regime where the gravitational waves are going to be detected in that case. The connection with the tidal love numbers becoming a zero and being, eventually found in the gravitational waves, which is the regime where they're not yet connected, is that this coefficients, this love coefficients or tidal deformations, when we compute the gravitational waves, they show up, and they don't show up at the first orders. They actually show up at fifth post-Newtonian order. So we would need a very big accuracy of the gravitational waves. But if they're zero or not zero, will signal in this gravitational wave now form that we have that we can distinguish between a neutron star or some other object and a black hole in particular. But as far as we know, this has not been detected yet. That is something we hope in the future will be a signal of, knowing whether that's a black hole or not. So.
Thank you. And I actually have a follow-up question. So in this case, what would be the best astrophysical type of a scenario to describe this? Because it's not only proportional to the spin, right? Like we might be able just to see for even non-rotating black holes. So based on your analysis, what will be the best scenario to go after measuring these quantities, for example?
I think accuracy of the gravitational waves would be the best, scenario in the system for the binary systems. If you insist in looking at, the gravitational waves, there could be other effects, right? Tidally deformed objects have other effects, right? There could be other effects that we don't see. So if you shine light and the tidal deformation is very, very big, then, well, you should see it, right? You should see that the object is tidally deformed. Now, it's not going to be, Alejandro, you're working on photon rings, right? So it's not going to be an evidence because the tidal deformation has to be really big in order to be able to see that effect, but probably there will be other effects in the environment. It could be that it has to do with the jets of the black hole that are different because the black hole, if you're in a binary, this is the system I'm thinking, like a binary system where the two black holes have jets and now they're tidally deformed. So they could have other type of emissions or signals. I don't know. So it's not all gravitational waves. Gravitational waves is a place where we could look at this.
And I have another question. I don't know if Roberto has a question. But then in this sense, has this been also been studied in just pure Newtonian systems, like this type of dynamical law of numbers? Like, I don't know if I want to think about even Earth and the interaction with the moon, the same, like, do you have an analog in just classical Newtonian? Because at some point I'm still digesting your talk, but then I'm not sure if it's a property of the black hole per se. Now it seems like
No.
special.
You're right. No, it's a general property. So what I wanted to say, and maybe I just so that I don't have to flush you through all the talk, is the way we can represent these tidal deformations in here is this is a Newtonian description. And this is the way you would, this is a spinning, so let's think about it in a different way. This is if you want, a mode decomposition, multiple mode decomposition of the perturbation of the geometry, and it could be a star. It doesn't even have to be a neutron star. So the first term is your point particle mass, and these are the multiple deformations. So what this means, this term versus this, is that this term here, this one that goes like R to the L, will be the effect of actually the external field that is sort of pulling you out. And this is the reaction, is the R to the minus L, if you multiply this R here in both places, is the effect of what is the effect in the geometry, the reaction to the external field. And so these coefficients here that are there should be a way to define the multiple, the quadruple, the octuple moments, and so on in general relativity. But this, besides the multiple expansion, these coefficients are universal. So they should apply for stars, which is the things that we do. Currently, and this is, Love was a math professor 100 years ago, and he started thinking about actually stars. Is there a way to define these Love coefficients in a way that if we look at them, we could say what are their internal decomposition, internal structures? And this is how we can give categories and know what the stars are made out of. Because if they're squishable and the coefficients are larger, then they're very squishable. They're made out of different materials, softer materials in some way.
Yeah. Okay. So my question was on this, because then it seems we can just go at a sort of Newtonian level. And I know, for example, there is a proof around Earth that I once saw a slide where they are able to measure the multiple moment of Earth, like L equal 300 something.
Yeah.
So in some sense, they should be able to be sensible to the dynamical changes of here. So maybe at a Newtonian level, you don't even have to think about black holes in that sense and go, okay.
So for the Earth, there are different ways. You know,
Yeah.
you have the say the solid part, and then you have the oceans, right? So the effects are different
Yeah.
internally and outside, and it's a more complex. You know, I was putting two objects next to each other, but in the solar system, you have all the different things, right? When we go close to the other planets, we feel the tidal effect as well, much harder than, or much more than if we're far away. So
Thank you, thank you. I received another question, and then it says like, are those symmetries related to a conserved quantity, the Love and the Starobinsky symmetries? Is there an easy way to understand them physically?
no, they're since these are hidden symmetries. So hidden symmetries are like you're cheating in some way. So we are saying, well, we see that this equation, the wave equation, does have this symmetry, but the geometry doesn't have it. So it's not realized. So we don't see that if we're moving, you know, or we are looking at the geometry, this is going to be a symmetry in there. And so conserved charges are defined through, you know, Killing vectors or objects that are in, you know, defined through the geometry. So there's no direct, you know, connection with the conserved charge for these symmetries in particular.
Let's see if there is a follow-up. Roberto, do you have a question?
Yes, I have one question. In fact, you just said one of the questions that I wanted to say to Maria about the conserved charge. Yeah, but I have another question kind of related, because due to this tidal effect, if I understood well, the event horizon of the black hole also changes, also gets deformed, right?
Yeah, definitely,
so this fact would modify, for instance, the typical signatures that people study or want to study for black hole, like Hawking radiation, or maybe it would change the entropy, the formula entropy for the black hole and the temperature.
Yes, it changes the tidal deformation, changes the temperature, the angular velocity, the entropy of your black holes, because the area of the event horizon changes. The whether you want to think about what the effects would be is, it depends how big the effect is. Does that make sense? So tidal deformations, even though I painted something like a, you know, American football kind of black hole, the effects are not that big. They're very tiny. Yeah, it's like the effect on Earth, right, of the sun. We see it in the ocean. We don't really feel it, right, when we are standing on the ground. And so in that is, I think that's part of the problem, that to see tidal deformations being meaningful is sort of what happens in the gravitational wave detection. You have to be to certain order in order to be able to see it. Say for the light going through, or, you know, jets in tidally deformed things, or as you were saying, other effects of being able to measure the temperature of the black hole. They're tidally deformed, so we can go take the geometry, compute the temperature changes, but the difference is going to be too small to detect. But yes, the effects are there, and there are solutions of Einstein's theory of general relativity. So here we're not doing, you know, anything, you know, new. It's not modified gravity. It's not that these solutions, these are really solutions. So by solving this equation, we're really solving the perturbations of the linearized Einstein's equations and the perturbations to the geometry. And those are valid solutions in there. The numerical people can do much better than what we're doing. We're doing linearized perturbations, and they can go, you know, do this like magical things and showing us this beautiful plots. So I'm sort of cheating. I'm exaggerating, if you want, the deformation, but the deformation is there. Yes. So it will have a physical, you know, kind of effect.
And two small question in the case because when one thinks like in the classical case, one of the effects that is typical from tidal waves or so on is the so-called tidal locking, in the sense that the two objects share the transfer angular momentum in order to remain face to face. So this would happen, but at the end of the, for instance, and close to the for the merging moment or something like that. Also with the Roche limit, that is when the self-gravity is going to evenly disrupt the object. I mean, would be some analogous case in this scenario.
Okay, let me clarify two concepts first. So tidal locking, what is it? So when we are on Earth, we see always the same phase of the moon, right? And this is due to the tidal deformations. And so they, the objects, meaning the moon and the black hole, they get tidally deformed. And so they tidally lock themselves in the orbit. So we always see the same phase. So the question is, do we see the same phase in tidal locking for black holes? Well, I think the regime for tidal locking is going to happen at very, very close epochs of the evolution. So I'm not sure the tidal effect of one black hole to the other, if we believe in general relativity, will be there for the binary system per se. I think that, you know, there could be that the spin-spin interactions are different or orders are bigger than what we see in the effects in here. For the Roche limit, this is kind of interesting. So what is the Roche limit? There's a limit where we think that matter cannot, so we have a compact object and we approach another compact object, say a star is approaching a black hole. And so there's a limit, there's a radius of a distance to the larger black hole where the object starts first spaghettifying, if you want, yes, and being tidally disrupted. That means the molecules or your atoms cannot be tight anymore together, and they start, like the star becomes this disintegrated object. Black holes don't have a Roche limit. So they're super stubborn. They will not do that. They will deform. And this is the interesting bit. These guys will never disintegrate. Black holes don't disintegrate like stars. They kind of go and merge very deformed. That's kind of the key in there. And so we'll see deformations. We'll see deformations of them. And this is what we expect if we, you know, can measure at that level of proximity of one black hole to the other.
Okay, thank you.
Yeah.
Awesome, thank you. We are way past the hour, but I want to ask you one last quick question. So in these terms, you have a logarithmic term that I don't think can appear in a post-Newtonian expression. Can you just elaborate? So is there a way to reconcile this notion of the static ones and then maybe do time-dependent perturbation in a la post-Newtonian in some sense? Will these terms appear in a post-Newtonian scenario? Can
They should. So what happens is, let me quick flash out. Alejandro caught the bit that is more kind of
technical,
interesting, if you guys want. So let me show it here. So the love numbers, when they're frequency dependent, when they're dynamical, have a log dependence on R. And so the question that Alejandro wants to ask is, and I haven't talked about here, is there are different ways of finding. So I was doing a purely gravitational computation, but these love numbers can be computed to post-Newtonian approximations in the geometry. And in there, people computing the love numbers from the post-Newtonian computation haven't found these log corrections, these corrections that are frequency dependent and as well have a dependence of log of R. And I think they have to be there, and not because I did the computation in GR, but also because when there's another way of representing these tidal deformations that I haven't talked about, which comes from what's called the effective field theory approach. So there's a way of representing the process of the binary system merging as point particles and world volume, so an effective description of the system with Wilson coefficients, where again we get perfect agreement between the love numbers, the dynamical love numbers, and the EFT computation that is very, very robust at this point. So in the post-Newtonian computations, they should be there. And I think they are. It's just that perhaps they're hidden in some way of things that have been perhaps discarded.
Thank you very much. And again, thank you very much for sharing your time here in one of the Law Physics webinar. We thank everybody that attended and everyone in the future that will see this wonderful webinar. And this was our first webinar of 2024. Keep stay tuned for the following ones. Thank you very much, Maria, for joining your time, and we hope to see you in another Law Physics webinar. Bye-bye, everyone.
Bye. Thank you. Thank you, everyone.